Hello everyone, today's topic is lightweight stream ciphers. First, I will talk about what a stream cipher is, the idea behind it, and then I will talk about some early broken stream cipher examples like RC4 or A51 or similarly Crypto1 algorithm. Then I will move on to current lightweight standards like Salsa, Cha-Cha, and Okore and Trivium algorithms. But let's start with basic idea behind the stream ciphers. In order to understand stream ciphers, actually we first need to know what a one-time pad is. So let's start with a one-time pad, which is also known as Vernam cipher. So idea is as follows. This is actually an unbreakable cipher, by the way. So it is always asked when people first start learning cryptography, they ask if we can design an algorithm that is unbreakable. And yes, we can design a cipher that is unbreakable, but we will see that it is not practical at the end. So this is stream ciphers will come behind from this idea of one-time pad. So let's start. Idea is as follows. Generate a very long sequence of random bits. This is going to be called a one-time pad. Actually, I'm talking about bits here, but this is a very old cipher. So initially what people did was to work on letters. So instead of bits, if you want to do it with a pen and paper, then you can choose a very long text, for instance, and using the English alphabet, randomly chosen letters. Then you can combine your plain text with this randomly chosen letters. But since we moved on to a digital age, it is better to talk about bits. But idea will be similar for characters too. So let's focus on bits. So generate a very long sequence of random bits. This I'm saying a very long. This actually means that it should be at least as long as the message you want to send. So if you want to, for instance, encrypt a 1 GB file, you need to generate 1 GB of bits, okay, random bits. Then what you do is as follows. Convert your plain text into, again, zeros and ones, write them in a binary, then XOR your plain text with this one-time pad and obtain the ciphertext. So it is as simple as that. So it's a single XOR operation of the whole data. You send the ciphertext to the person you want to communicate, and they also have the one-time pad, so they XOR their ciphertext with their one-time pad and obtain the plain text back. So this is the idea. An example is as follows. If you don't know what an XOR operation is, it is actually short for exclusive OR operation, which is actually addition modulo 2. So assume that you converted your plain text into zeros and ones. Then you randomly generated a one-time pad, which is again zeros and ones, but this doesn't mean it is randomly chosen. What you do is actually perform an addition operation column-wise where you don't have any carry bits. So the result will be something like this. For instance, when you XOR 0 and 1, you get 1, like a regular addition, or adding 1 to 0, you get 1. Only difference is that when you XOR 1 with 1, you get 0, but you don't have a carry bit here. So the additions are column-wise because it is a bitwise addition, a binary addition. So in order this to work, the one-time pad should be truly random. If there's an algorithm behind it, if the attacker can guess what it is, then the system is broken because they can get one-time pad. So the whole security relies on the fact that one-time pad is generated in a truly random way, and it is not shared with anybody else. And another important thing is that you can only use a one-time pad only once. This is why we call the one-time pad actually. You have to use it only one time. And Shannon proved that this provides perfect secrecy because ciphertext provides no information about plain text. The guessing the plain text from the ciphertext would be equivalent to guessing the one-time pad in the first place. So this is why we believe that it is secure. Actually, Shannon proved it. Instead of working with bits, one can work on letters or characters. So if you go back, if your first letter is A, in English letter, you can represent it as 0 because in modulo 26, A would be 0, B would be 1, C would be 2, and so on. And you add your letters together, and if it exceeds 26, you will perform a modulo 26 operation and write it there. So idea is as simple. You can even use a pen and paper and perform this operation. Usually the secret key, which is in this case a one-time pad, is printed on a single page with very small letters. This is why the name is called a one-time pad. That is the historical reason, actually. And although this is unbreakable, the problem is that the key is very long. You have to generate a truly random key, which should be as long as the message you want to send, and it should be transferred to the people you want to communicate with beforehand. So for every message, you had to generate a one-time pad and transfer to the people you want to communicate. And this causes a key distribution problem. And another problem is that you have to generate them in a random way, and doing it in a random way is not that easy. We have random number generators and so on, but still, it is not an easy task. So what is the weakness of the cipher? We already mentioned that the one-time pad should be only used once. If you reuse it, it causes a problem. Consider it like this. So if the adversary captures two ciphertexts C1 and C2, which were generated with the same key, then they can compute this. They can XOR the C1 and C2, which they captured, and they assume that these ciphertexts are obtained by one-time pad, which is used twice. So this would actually mean, since C1 is actually the XOR of first plaintext and the key, one-time pad, and C2 is actually second plaintext XOR with the same key. So if you XOR C1 with C2, this would mean the XOR of this whole thing, but Ks will cancel each other because this is an XOR operation, so 2K will be actually 0. So because this is a modulo 2 addition. So the result would be P1 XOR P2. So people capturing the ciphertext would have the XOR of the messages. So you might think that, okay, this is not the message P1 or P2, but they're XOR. But since the language has redundancy, where a lot of letters are repeated, for instance, in English, E is repeated the most with, I think, 11% or something. In Turkish, it is A with 12% and so on. So from this, you can capture parts or the whole of P1 and P2. So this is why you cannot use the same one-time pad twice. And in the history, we have a lot of examples where people broke messages because other people used one-time pad twice. So the thing is that this is a good idea, but it is not practical. We cannot generate that many keys and so on. But this actually leads to the idea of stream ciphers. Stream ciphers try to achieve the one-time pad-like security by generating a pseudo-random key stream from a short key. So instead of choosing a very long one-time pad as the key, use a short key like 128 bits and design an algorithm so that from this short key, we can produce a very long, randomly rooking zeros and ones, which we will be calling key stream, and use it instead. So this would be the main idea behind stream ciphers. So let's start. Symmetric key cryptography ciphers can be divided into two. Symmetric key crypto systems are classified as block ciphers and stream ciphers. Actually, I would like to add sponge construction here as the third case in the future, because for me, it is kind of different than these two. But anyway, let's focus on these two. Block ciphers operate on large blocks of plain text data with a fixed transformation. And here, actually, misconception occurs. Since it is called block ciphers and it works on blocks, and most of the stream cipher work on bits, people think that this is the only difference between block ciphers and stream ciphers. I even see master or PhD theses where people define stream ciphers or make the classification as follows: block ciphers work on blocks, stream ciphers work on bits. This is completely wrong. There are a lot of stream ciphers which actually works on blocks. Okay, so the difference is not that. Stream ciphers operate on individual plaintext digits. which can be as small as bits, but it can be as long as maybe 128 bits. But it operates on them with a time-varying transformation. And moreover, we will see that STEAM ciphers have some kind of a memory, which we will be calling the internal state. So that is actually the main difference. So a block cipher processes the plain text in relatively large blocks at a time, and the encryption function is same for every block. So we can see it as a bijective function f, where it takes two inputs, the plain text and the key, and produces the cipher text. Some mode of operations can turn a block cipher into a STEAM cipher. We will talk about them in a minute. But a STEAM cipher processes the plain text in small blocks, sometimes as small as a single bit. Contrary to a block cipher, a STEAM cipher has a memory that we call the state at the time t, and it processes and it changes as it processes the plain text. So it is a time-varying transformation. This state is an input of the encryption algorithm. So we can consider a STEAM cipher as a pair of functions f and h, as f is the next state function. So whenever you run this function for one tick, let's say, from the current time t, the internal state, the plain text, current plain text digit and the key material is used, and the next state is obtained. So with this way, you update the internal state. But there's another function that we named here as h. It also takes the current state, the current plain text digit, the key, and produces the ciphertext. So this is the main difference between block ciphers and the STEAM ciphers.